quantum cryptography is much more than what we've seen so far. Unfortunately, we don't have the time to discuss all protocols in quantum cryptography in the course of this class. However, this week we will discuss a few select topics where quantum communication is very useful to solve other cryptographic tasks. Let's start with something that is known as position-based cryptography. As you may have guessed, it concerns itself with using the position in space as a credential. Sometimes we may wish to send messages which can only be read at someone at a certain location. For example, I might want to send a message to my colleague Ronald, who you met earlier, such that it can only be read if he's actually at QTech. A simple task in this regime is just to verify the position of someone. And this is what we will focus on in this lecture. Imagine again our tireless protagonists, Alice and Bob. Alice and Bob want to convince themselves that Waldo is at a particular position. Therefore, implicitly, we will just consider the position on a straight line connecting Alice and Bob. That is, Alice and Bob already know Waldo is somewhere on that line, but are unconvinced where exactly that is. More specifically, we want to solve the task of position verification. Let's suppose that Waldo claims to be 1 kilometer away from Alice and 2 kilometers away from Bob. Call that coordinate 1, 2. How can Waldo convince Alice and Bob that he's really there? And how can Alice and Bob be sure that he doesn't trick them? As you might have guessed, there's again two demands to our protocol: correctness and security. We call a protocol correct if honest Waldo really sits at position 1, 2, then Alice and Bob would actually believe him. In contrast, our security demand will be that if Waldo is not at the claimed position, then Alice and Bob will surely catch him. So what resources do Alice and Bob have available to track down Waldo? First, we will assume that Alice and Bob know their own positions relative to each other. In other words, they have some sense of the coordinates that Waldo might occupy. Second, Alice and Bob will at some point be able to exchange secret messages without the knowledge of Waldo. For example, they might be able to do so before the protocol in order to exchange some classical randomness unknown to Waldo. To have any hope of checking on Waldo, we will also give them classical and quantum communication channels during the protocol. Alice and Bob will also have highly accurate clocks, and they can use these clocks to measure very accurately the time between sending and receiving messages, for example. Alice and Bob also know how long messages take. To achieve correctness in our protocol, we will assume that there are no unforeseen communication delays. If Alice sends a message to Waldo, it will arrive there always after a fixed time. If you want, take that time to be given by the speed of light. The speed of light is indeed the maximum velocity at which information can travel. So we will also assume that there's no way any of them, including of course Waldo, can communicate faster than the speed of light. So why are these useful resources? Let's have a look at the effect of message delivery times and Alice's ability to verify Waldo's position. I will draw here what is called a space-time diagram. We have the position in space, here just a line from Alice to Bob, but we also have a position in time, given by this time axis. You can think that all parties are always moving through time, even they might be stationary at a fixed space location. In such a space-time diagram, we can draw a so-called light cone. If Valdo is at any location within Alice's light cone, then he can receive a message that Alice sent at this point in time. Let me call it t equals 0. So if Valdo is here, it is possible for Alice to send a message. If Valdo is in the light cone of both Alice and Bob, then he can receive messages for both of them at this particular time. If he's closer to Bob than to Alice, then it might be that he's outside the light cone of Alice. He can receive a message from Bob, but he cannot receive a message from Alice because that would lie outside her light cone. This just means that it takes a certain amount of time for information to travel from Alice to Valdo. So why is this useful? Let's go and ping Valdo. Let's just have a look at the messages from Alice. And let's imagine that she sends a message to Valdo at this point. Call that t0. I'm calling her Alice1 to emphasize that this is at time 0. If Valdo is inside her light cone, say at this position, then he can receive a message from Alice. He could also immediately send a message back to Alice, and if Alice is in his own future light cone, she's able to receive it. So Alice is able to receive the message at this time, t. However, if Valdo was actually further away from Alice, then he receives Alice's message much later in time, because information can only travel at the speed of light. So he will only get the same message much later. So if he now sends something back to Alice, that at this point in time Alice is outside the light cone of Valdo. So if Alice is not in there, there's no way for the Valdo at this point in time to send anything to Alice. We can thus go and ping Valdo. Alice sends him a message and looks whether she gets a reply within a certain time frame t. If she does get an acceptable reply within the time frame, then she knows that Valdo must have been decently close to her. So you might be asking, is position verification not totally easy then? Alice and Bob could send some coordinated messages to Valdo and see when he replies. From this timing information, they could verify his position. Or can they? We are certainly in good shape if there was only one Valdo. However, in the security analysis of position verification, we will assume that Valdo can indeed enlist the help of his friends, in particular his friend Wenda. Together, Valdo and Wenda will claim that they are at position 1, 2, while actually both Valdo and Wenda are located elsewhere. Can we hope to construct a protocol in this setting if Valdo can use the help of his friends? It turns out that this is highly non-trivial. In particular, even a classical protocol that makes computational hardness assumptions cannot lead to security. It has been proposed to solve this problem in classical communication and bounded classical storage or bounded retrieval, but of course storing classical communication is not particularly hard. In the coming videos, we will see that we can, however, construct a quantum protocol under the assumption that it is difficult for Valdo and Wenda to store qubits, limiting the entanglement that they might share. So let's go and have a look.